this evening, it really is a big pleasure for me to introduce this evening's speaker. I've known her since about 20 years. She's been a physicist at CERN since about 1984. But before that, she got a baccalaureate and a degree in music. So you might wonder, how do you get from music to physics? But she got a PhD from the University of Milano in 1989, working on an experiment in CERN. She has a number of honors. She's a doctoral degree from an honorary doctoral degree from Uppsala University in Sweden. She's a member of the Italian Academy of Sciences. That's a relatively young organization. It was formed in 1603. In September 2012, she was given the honor of Grande Ufficiale by the Italian president, Giorgio Napolitano. And then maybe most remarkable of all, she was runner-up in the 2012 Time magazine Person of the Year. Of course, the winner would take some beating. If you remember correctly, it was President Obama was the actual winner. So coming runner-up to the president isn't a bad show. So Fabiola was spokesperson, spokeswoman for the large experiment, the ATLAS experiment at CERN, which discovered the Higgs particle. And I'd like you to please join me in welcoming Fabiola Gianotti.
Thank you so much. Thank you. Thank you, Steve. So thank you so much to the lab director for this nice presentation. I'm really pleased to be with you tonight and to share with you the excitement for a very special discovery, the discovery of the Higgs boson, which represents a big step forward in our understanding of fundamental physics, and therefore the structure and the evolution of the universe. And I will also try to discuss tonight what is the possible impact of the Higgs boson on our life. And I'm very pleased to do it here at Jefferson Lab, because this is a laboratory where they do a lot of fundamental research, but with many applications to society. So I think it's a very good place to discuss these things. So the Higgs boson was discovered at the Large Hadron Collider, which is the most powerful accelerator ever built by mankind, the highest energy accelerator, and is located at CERN. So let's make a step back and discuss a bit about CERN. Perhaps you know that CERN is the biggest laboratory in the world for particle physics. It's located in Geneva, in Switzerland. It's a very special place where, over the past 50 years, scientists from all over the world have been doing research, fundamental research, awarded by discoveries and Nobel Prizes to several scientists working on CERN experiments. It's a place where the scientific goals require the development of cutting-edge technologies in a huge number of domains, which are then transferred to society. One example is the World Wide Web, which was introduced at CERN exactly 20 years ago. So happy birthday, World Wide Web, by Tim Berners-Lee, to facilitate the exchange of information among the scientists involved in the laboratory experiment. And of course, since then, it has changed the way society accesses information. And I will give you many other examples later on. CERN is also a place where we train people, tomorrow's scientists, but also school teachers and students through a huge number of activities and initiatives. And it's also a very nice place to bring bring nations together by attracting more than 10,000 scientists from more than 60 different countries. So a little bit of history. CERN was founded at the beginning of the 50s with a twofold goal of, on one end, to give back prestige to European research and science after World War II by creating a center of excellence, at the same time to mitigate the tension of the Cold War. Today, it's a global laboratory. It consists of 20 member states. All of them are from Europe, but there are nations from all over the world with different status, non-member states in general, but also observers like the United States. The budget amounts to something like $1 billion per year, and each member state contributes to this budget in proportion to their income. So $1 billion per year means, on average, 1 cappuccino per European citizen. I stress on average because it changes with the latitude. So in Southern Europe, like Italy, the cappuccino is very good and very cheap. And then you go north. In Sweden, for instance, it's extremely expensive and, okay, very bad. Okay, so this budget is used to, in part, to pay the salary of the staff, of the employees, about 2,000 people, and in large part to develop the infrastructure, so the accelerators and other infrastructure, which is used by the worldwide community to do experiments at CERN. And this worldwide community consists, as I mentioned before, of more than 10,000 people from all over the world, more than 60 different nationalities and countries. So you can see in blue member states, European states, in green observer states like the US. And actually the US contribute the largest contingent of scientists with 1,700 people. So the US is contributing a lot to CERN activity, but is also benefiting a lot from activities at CERN. And then, of course, there are scientists from all over the world: Australia, South Africa, China, South America, etc. So, but beyond these social considerations, the primary mission of CERN is, of course, science. So what we do, we study the elementary particles, among which the building blocks of matter, electrons and then quarks, and the forces that control their behavior at the most fundamental level. So today we know that matter is made of atoms. Atoms are made of a central nucleus surrounded by a cloud of electrons. The nucleus in turn is made of protons and neutrons and neutrons are made of more elementary particles called quarks. As far as we know today, quarks and electrons are elementary particles. It means that they cannot be broken into smaller pieces. And they are the fundamental constituents of matter. So everybody in this room, you, me, this little high-tech gadget, this microphone, everything is made of electrons and quarks. Now, experiments at JLab and CERN allow us to understand the structure of the proton and neutrons and also how quarks interact. In particular, at CERN, we are able to scrutinize matter by using the Large Hadron Collider, the most powerful accelerator that we have today, down to scale of 1 billionth of a billionth of a meter, so 10 to the minus 18 meters. So you have to consider this big accelerator as a giant microscope that allow us to scrutinize, to probe matter down to its most elementary constituent. At the same time, these studies allow us to give us indication about the structure and the universe, structure and evolution of the universe. So the very small allow us also to understand the very big. And the reason for that is the following. We know today from cosmology and also from several experimental observation, space mission, etc., that the universe had origin through a big explosion called Big Bang. And at the beginning it was very hot, and then with time it expanded and cooled down. And during the cooling, at the beginning, after the Big Bang, the universe was essentially gas of elementary particles, of free elementary particles. And then with time, with cooling down, particles started to stick together to form nuclei and then atoms, and then little by little the macrostructure that we know today, like stars, planets, galaxies, etc. So by studying the particle physics in controlled condition at accelerator, we can reproduce the state of the universe at the very beginning when it was a gas of elementary particles, and so understand how the universe evolved, what kind of forces were at play, and what kind of phenomena, etc. So what do we do in practice? So we do the following things. We accelerate, at least at the LHC, we accelerate two beams of protons in a ring, and we make them collide. And in the collision, the following things happen. So what I'm going to say now is scientifically not rigorous. So I'm trying to be very simple. So I hope that what I'm going to say remains in this room among ourselves. Well, there is a camera, but I hope that I'm a bit worried by the camera. But anyway, otherwise I will be fired as soon as I'm back at CERN. So in the collision, you can imagine the protons go into thousands of pieces. They break. Okay, these are very high energy collisions. So you can imagine they break into thousands of pieces, like when you collide two Ferraris at full speed. And in this way, we can study the elementary components of the protons, so the quarks, and the way they interact. So we can study the behavior of elementary matter constituents at the most elementary way. So this is the first goal. Second goal, the energy which is produced in the collision can transform itself into particles. We all know the famous Einstein equation, E equal mc squared. So energy can transform itself into matter, matter can transform itself into energy. So you have energy, you produce new particles, and the higher the energy of the accelerator, the energy of the collision, the more massive can be the particles that you produce. So particles which have not been discovered so far because a previous accelerator may become accessible, may be discovered today at the most modern accelerator and most powerful accelerator that we have built. So then what we do, we surround the collision region with powerful instruments that we call particle detectors that allow us to detect the product of the collision, the particles that are produced in the collisions, and therefore to understand what happened in the collision itself. So what kind of phenomena were involved, what kind of forces, etc. So we need, therefore, three fundamental things, actually four. The first thing we need, of course, is brain, ideas, and people. Okay? But apart from that, we need three main instruments. We need accelerators, we need particle detectors, and we need powerful computers. So accelerators usually are underground rings like this one. So this is a view of the LHC. It's a ring, it's a tunnel, and these blue objects are actually magnets. Accelerator contains two main elements. They contain electric field, which are used to accelerate particles incrementally at each turn. So at each turn, you give them a kick, and they get accelerated until they reach the final energy. And then magnets. Magnets are used to guide and to steer these beams and to the particles and to keep them inside the ring. Detectors are instruments, so are high-tech devices that we use to essentially cover the full solid angle surrounding the collision points, and they are used to reconstruct the trajectory, ideally, of every particle produced in the collision, measure its energy, identify this particle, understand if it's a photon, an electron, or another particles, and then get a full picture of the collision event. And then once we have the full picture of the collision event, we can interpret it and try to understand what happened in the collision. And then we need computers to store, distribute, and analyze the vast amount of data produced by this instrument. Now, the most powerful accelerator, but also the most high-tech and complex detector and the most advanced computing infrastructure ever achieved in accelerator-based particle physics have been conceived and built in the framework of the Large Hadron Collider, the LHC, which actually is one of the most ambitious projects in science ever and more in general. It has required the 20 years of efforts of the international community and many innovative concept technology that we have to develop in many domains, from cryogenics, new materials, electronics, etc. So what is the LHC? The LHC is a 27-kilometer ring located 100 meters below ground across France and Switzerland. So this is an aerial view of the region. Here you can see Geneva Airport. These little dots indicate the border between Switzerland here and France here. Lake Geneva is down here. This is CERN main site. I live here, but you don't care, okay? So this circle indicates the location of the LHC accelerator. You can see it on the surface. It's underground, 100 meters underground. So over the past 4 years, we have been circulating 2 beams of protons in the 2 opposite directions, accelerating them up to almost the speed of light, and make them collide at 4 points of the accelerator, where 4 enormous big particle detectors had been installed in very big underground cavern, and these detectors are there to detect the results of the products of the collision. So these detectors are shown here. They are called ATLAS and CMS. ATLAS and CMS are the 2 biggest ones. These are the 2 that have reported the discovery of the Higgs boson. And 2 other ones, smaller one, LHCb and ALICE. The US, through laboratories and universities, has contributed a lot in a very crucial way to the construction of both the accelerator and the 4 experiments, and also to the physics exploitation of the data, and in particular to the discovery of the Higgs boson. So this is one of these experiments, ATLAS, actually the one in which I've been working for many years. So notice the size of this detector. So this is a human being. So you can see it's 45 meters long, 25 meters high, so it's almost a 5-story building. The 2 beams collide here in the middle. So you may ask why it's so big? Because if you want to measure in detail, absorb the particles that are produced in the collision, if this particle have high energy, like the energy of the particle produced in the LHC collision, you need very big volume and very massive detectors. At the same time, these detectors have to be extremely precise, because we want to reconstruct the thousands of particles that are produced at each collision with very high precision, micrometric precision, where 1 micron is 1 millionth of a meter. So we need a lot of very individual sensitive elements, individual signals, in order to be able to track the individual particles produced in the collision. And so for this reason, we have 100 million individual electronic channels from which we have to extract, we extract the information coming from the collision. So the type of information that actually we can extract and we can reconstruct is the following. This is an event, a real event, that has been recorded by the CMS experiment. So the 2 beams have collided here. So this is the collision point, and you can see the various particles emerging from the collision. Actually, not all of them are shown, because usually there are many more. And you can see the individual signal, hits as we call them, released by these particles, or the energy, the release in the various elements of the detector. And you can see that almost by eye, you can reconstruct the trajectory of the individual particles and measure their energy and identify them. So these detectors can be seen like giant digital camera, which take pictures of the collision. But the problem is that the proton beams collide 40 million times a second. So this camera have to be ready to take 40 million pictures a second. Of course, we don't store 40 million pictures a second, because we will not have the technology to analyze all these pictures. We just store a small fraction of them, but nevertheless, the detector must be able to react to 40 million collisions a second. So it's quite challenging. So it was also a very challenging and demanding engineering enterprise. What you see here is the underground ATLAS cavern, as it was in June 2003. At that time, the civil engineering excavation work had finished, was terminated, and the cavern was handed over to us, to the experiment, in order to start the detector installation. So we started by, well, you see it was pretty empty. And then we started to install the infrastructure of the experiment, and then the big elements like these big, enormous magnets coiled. These are 100-ton objects, each 25 meters long. You see again a human being here. And in October 2005, a large part of the detector was installed. And again, you see the complexity and the size of this amazing detector compared to a person. Now, also impressive is the size and the geographical spread of the scientists participating in this experiment. In ATLAS, we have 3,000 scientists from all over the world, coming from 38 countries. So in yellow here, you can see the map of the ATLAS population. We have people from Europe, from the US, from South Africa, from Australia, China, Taiwan, South America, and etc., all working together peacefully. From the US, we have about 40 universities and laboratories, a total of 600 scientists, and note that more than 250 are PhD students, so very young people. And the US, as I mentioned before, has made very, very strong contributions to the detector construction, to the construction of ATLAS, to all components of the experiment, including the software and the computing, and to the analysis of the data, and including the Higgs discovery. So I would like to show this plot which gives you the distribution by age of the ATLAS population. So the age of the 3,000 physicists that I've shown before. In blue for boys, and in red for girls. And you can see several things. First of all, that most of the population is young. Out of the 3,000 scientists, more than 1,000 are students, so more than 1/3, and actually they are the driving force of the experiment with their enthusiasm, their competence, and their energy. You see also that we have also many postdoc, of course, and you see that most of the population is below 40. Say, I'm here, of course, in the first B. Don't laugh; it's not kind. But anyway, and you can also notice that the fraction of women is at the level of about 20%, but this fraction increases among the young generation. So there are more and more women among the young generation starting doing activities in fundamental research, which is, of course, very nice. Okay, I will skip the computing part and just give you a few additional numbers and then go to the main topic. So the protons run in the LHC ring close to the speed of light. To be precise, the speed of light is minus 30 kilometers hour. And so they are able to do 11,000 complete tours of the ring, 27-kilometer ring per second. The beams contain 100,000 billion protons. The transverse size of the beam is very small, about 20 microns. This is smaller than the human hair. And in order to steer the beams in the accelerator, we use high-tech superconducting magnets, which work at 2 degrees, 1.9 Kelvin, so 1.9 degrees from absolute zero is minus 271 degrees Celsius, which makes the LHC, the 27-kilometer ring, the coldest place of the universe, because the outer space is at 3 Kelvin, whereas we are working at 1.9 Kelvin. So we used to say that the LHC is very cool. And this energy, the beam have a very high energy because they have a lot of protons at very high speed. So the energy stored in the beam is 350 megajoule. If you want to know what this means, I read that this is like the energy of a British aircraft carrier traveling at 12 knots. I don't know why it has to be British, cannot be American, but okay, this is what they said, so I'm just reporting what I read. The CMS experiment contains more iron than the Tour Eiffel in Paris and weighs more than it. In ATLAS, we use 3,000 kilometers of cables to bring the signals from the underground cavern, from the detector, to the control rooms. And every year, the LHC experiments produce an amount of data of the order of 10 petabytes. Everyone knows what a petabyte is, but in case you don't know, if you want to write this data on DVDs, you need a stack, which is 20 kilometers high. So the question is why? Of course, why this, say, quite complicated initiative and project? So the reason is the following. So the elementary particles and their interactions are quite well known today, thanks to almost 40 years of experimental work at CERN, at JLab, at SLAC, Fermilab, many other laboratories all over the world, in particular in the US. So we have discovered many elementary particles. We have studied their interactions in all details. We have also a theory called the Standard Model, which describes the elementary particles and their interaction, which is extremely successful because all the particles predicted by the theory have been discovered. The last one has been discovered at CERN in July last year, is the Higgs Boson. And all the predictions in terms of interaction among the particles, behavior of these particles, made by the Standard Model have been verified by the experiment with very high precision. So clearly the Standard Model is a theory that works very well and is a correct theory. It is correct, however, it is not complete. It's not complete because it's not able to answer several questions that experiments or also some theoretical ideas have raised. Some of the questions are listed here. The first one is, what is the origin of the particle masses? This question is related to the Higgs boson, so I will come back to it later. And now we are ticking it off because we have an answer. But there are many others. As you know, the matter I was talking before, quarks, electrons, etc., atoms, accounts only for 5% of the matter energy content of the universe. The rest, 95%, is unknown. In particular, there is a 20-25% which is made of a form of matter that we are not able to detect, called dark matter. We detect it indirectly through the motion of the galaxies, but none of the elementary particles predicted by the Standard Model and discovered so far and that we know has the good feature to explain the universe dark matter. So there must be some new particles or new physics that explains this big fraction of the universe. We don't understand why in the universe there is so little antimatter and so much matter. Thank goodness, otherwise we will not be here. But it's a question that the Standard Model, again, we are not able to explain. We don't know if there are additional forces in addition to the 4 forces we know today, etc. So DLHC has been built to address these and other fundamental questions. And today we can say that we have answered the first one. So the adventure started in March 2010 when the first proton-proton collision at the highest energy ever achieved have been produced at CERN. And since then, the accelerator, the detectors, and computing have been working very well. We have essentially measured all the Standard Model, most of the Standard Model particles, the already known particles in details. We have explored also many scenarios to look for new physics which could explain, which would address the questions I mentioned before. For the moment, we didn't find anything. But what is most important is that last year we have reported the discovery of a new particle, which at that time we called Higgs-like particle, because we were not sure that it was really the Higgs boson. Today we have dropped the like, not because we don't like it, but because we think it's the Higgs boson. It has a mass around 130 times the proton mass. So this particle allows us to answer the question about what is the origin of the particle masses. So the question is the following, that we didn't know until the 4th of July last year why the photon, which is the constituent of light and which is responsible for transmitting at the elementary, microscopic elementary level, the electromagnetic force, why the photons is massless, it's just energy. Whereas other particles, like the W and the Z particle, which transmit at the elementary level the weak interaction responsible, for instance, for radioactive decays or thermonuclear interactions in the sun, the W and Z particle are massive. They have a mass of 100 times the mass of the proton. Why the heaviest elementary particle ever observed, the top quark, which was discovered at the Hadron Collider at Fermilab near Chicago in 1995, has a mass comparable to that of a gold atom, whereas the electron mass is 350,000 times smaller. So this was not really understood. So in order to understand how some particles can get a mass and other, like the photon, can remain massless, at the beginning of the 60s, a group of theorists, among which Peter Higgs, a Scottish theorist, but with some other collaborators, introduced a mechanism which got the name of Higgs mechanism. And I will try to explain it to you now in a very simple way. So how this elementary particle got a mass. So imagine the universe just at the moment of the Big Bang. So at that time, all particles were massless, just energy. So they were going around the universe, traveling at the speed of light as any massless particle like the photon. So the universe, after the big explosion, starts to expand and to cool down. And at some point, and this point happened 100 of a billion of seconds after the Big Bang, the temperature goes below a certain level, and the universe changed shape. Imagine before, just after the Big Bang, imagine that the universe is permeated by a medium, which we call a field in physics, but this medium is transparent, like ether, and the particles do not see it. So they go around at the speed of light, and they don't see this medium. But 10 to the minus 11 seconds after the Big Bang, the universe experienced what we call in physics a phase transition. Phase transition is a complicated term to indicate, for instance, when water becomes ice or vapor becomes water. So we go from gas to liquid, from liquid to solid. So the transparent medium becomes, when the temperature goes down, becomes a bit more consistent, a bit more solid. Imagine some jam, some marmalade, something like that, okay? At this point, the elementary particles start to see that is something. It's not just a transparent thing, there is something. So imagine the particles now like small balls. If the surface of the ball is smooth, then the particle will continue to go through the jam without noticing it. And this is the photon, which remains massless. If the surface is rough, then these particles start to stick some jam, and then more and more, and so they become fatter and are slowed down. So this is the mechanism. At some point in the evolution of the universe, the Higgs field became active, and particles got mass through interaction with the Higgs field. Okay. This is a wonderful thing. The problem is that this mechanism predicted the existence as a consequence of this mechanism of a new elementary particle called the Higgs boson, and this Higgs boson has been looked for over the last 40 years and has not been found until July last year. And so with this discovery, we have demonstrated that this mechanism is the correct one. So now, I'm sure that you are going to ask now a very legitimate question. And the question is, who cares? Who cares if the elementary particles got a mass 10 to the minus 11 seconds after the Big Bang, etc., if the electron has a mass which is 350,000 smaller than the top quark, etc.? Well, we do care, because if the elementary particles did not have the masses they have, the atoms will not stick together. The proton may decay. If the proton decay, there are no atoms, no chemistry, no nothing. So if the elementary particles, we are what we are because the elementary particles have exactly the masses they have. Just a tiny deviation in the mass of the quarks could make the proton decay. If the proton decay, we decay. So there is no universe, or perhaps the universe may exist in a completely different shape. So the problem is that this question is very fundamental, but until the 4th of July last year, we didn't know how this happens. So what did we observe? The Higgs boson was produced in the proton-proton collision, and it decays, it disintegrates immediately. For instance, it can decay into two photons, which are with which we are all familiar, and photons are the constituent of light. So what we did, we look at our recorded events with 2 photons in the event, and then we look at their spectrum. And if you have a new particles produced, then you should see a kind of bump, a kind of spike in the spectrum, and you see here this little bump. This is the result of the production and decay of the Higgs boson. This is one event how it could look in the CMS detector. So the 2 yellow lights indicate the direction of the 2 beams. They collide here. You see several particles coming out, and these green lines indicate the energy deposited in the detector by the 2 photons. We have also observed the Higgs boson in the decay into 4 electrons. Again, electrons are also very familiar to us in the day-by-day life because, of course, they are the component of electric current, for instance. So this is an event recorded by ATLAS which is probably due to a Higgs boson decay into 4 electrons. And you see here these 4 signals are the tracks or the energy released by the 4 electrons in the ATLAS detector. It was not easy to find it because one of these events is produced every 10,000 billion proton-proton collisions. So it was a very meticulous experimental work to try to extract this very tiny signal from the Higgs boson from the bulk of the proton-proton collisions. So I'm now going to go through 3 frequently asked questions. I have 5 more minutes and then I'm done. So the first question is the following. Is this new particle the standard model Higgs boson? So our present measurement, our present data tells us that it's pretty much like the standard model Higgs boson. So it has all the features of the Higgs boson. Now, of course, we will continue to measure it, to measure all these properties with the data that we have recorded so far, but also in the coming years with the data that we will record in the future. So, and we'll try to measure its properties with higher and higher precision to be able really to draw a definite conclusion. Of course, it could be the standard model Higgs boson. It could be a Higgs boson of another more complete and more rich theory than the standard model, a theory which could answer some other questions, those that I listed before, for instance. So a more exotic object, and of course we will much prefer this second solution because it will indicate the existence of new physics. Second question, is the task of the LHC over with the discovery of the Higgs boson? And the answer is, of course, no, because as I mentioned before, the LHC has been built to address many questions. We are ticking off now the first one, but there are many others. Dark matter, matter-antimatter asymmetry, additional forces, and so on and so forth. So we will continue to work in order to be able possibly to, if not to answer, at least to be able to make some progress in addressing the other questions. And finally, will the Higgs boson change our life? And the answer here, in my opinion, is that it did already. Perhaps you didn't realize, but it did already. And the reason is that the extreme performance that are required by particle physics and nuclear physics require the development of cutting-edge technologies in a huge number of domains. And so laboratories like CERN, like JLab, and many other, we have to develop new concept, to promote innovation in order to be able to meet our scientific goals. And of course, these developments find a lot of application in many domains. So I already mentioned the World Wide Web. Again, happy birthday to the web. But also in many other domains. So, for instance, in the world there are 30,000 particle accelerator, and more than half of them, 17,000, are used for medical applications. So, for instance, for cancer treatment, for bombarding the cancer cells. All these accelerators used for medical application are based on the technologies developed at CERN, at JLab, and many other laboratories. So this is an example of application. The technologies developed for particle detector instrumentation, for particle detectors and instrumentation, are used today for medical imaging, for instance, for scanners and things like that. So there is a huge number of benefits to society that we had to develop. So in order to discover the Higgs boson, we had to go through the development of many technologies that are already being used by society. So in conclusion, at CERN and with the LHC in particular, but not only at CERN and not only with the LHC, we are looking for answers to fundamental questions about the elementary particles and their universe. To do so, we have to develop new technologies and advance the frontier of knowledge, also of application, of course, to the benefit of society. We have very experiments with many young people, so training is also a very important mission in our field, and of course we have people from all over the world. So it's very nice to foster peace among people coming from countries which do not entertain a romantic relationship like Israel and Palestine and Taiwan and China, etc. And the scientists from these countries work at CERN in other lab together, and this is a very good demonstration of concrete demonstration of peace. With the advent of the LHC and exploration of the new energy regime, a new era of discovery has started, and of course the first very special and important groundbreaking discovery has been the observation of a Higgs boson, which represents a big step forward in fundamental knowledge. So I've been stressing a lot the application and the social benefits of fundamental research, but I would like to stress that fundamental research justifies it by itself for two reasons. First of all, because fundamental knowledge is the fuel of progress. If you don't advance knowledge, if you don't have a new idea, at some point progress will stagnate, become sterile, and so there will be no progress any longer. And second, because knowledge as art is among the highest expression of the human beings are clever beings, which distinguishes us from animals. So, should we stop supporting, funding art because it doesn't have an immediate benefit on our day-by-day life for buying bread or something like that? An Italian poet of the 13th century, Dante Alighieri, wrote "Fatti non foste a vivere come bruti, ma perseguir virtute et conoscenza," which means you were not born, you were not created to live as brute, as animals, but to pursue virtue and knowledge. So we should really support art, knowledge, fundamental research. Otherwise, we risk to alter the nature of mankind and human beings. Okay, I think I stop here. Thank you. Yes. Okay, so according to the program and to the instruction that I got, at this point I should ask you, are there questions? Do you have any questions? Yeah, so here and there. Okay, so please go ahead.
Amount of data per collision, is there a backlog of analyzing that?
It's a very good question. So the data are stored. First of all, the data are recorded by the detector. Then they are calibrated, and then they are reconstructed at CERN, processed at CERN, and where we go from the raw data, so from the individual signals coming out from the individual channels in the detector to physics objects, an event which has electrons, photons, and other particles. And then the data are distributed to all over the world, to all the institutions collaborating in the experiment. Typically, if you were to export the data immediately, as we did usually at the beginning, this takes 7 hours. Within 7 hours from data taking, the data are dispatched all over the world, so it's very fast. However, it's also true that from time to time, when the accelerator is working extremely well, so with a very up time during several days, there is some backlog. But then it also happened that, of course, from time to time, the accelerator stopped for 1 and 2 days, and so we can catch up on the backlog. That is a very good question indeed. Yeah?
With the Large Hadron Collider, you were able to generate enough energy to discover the Higgs boson. Now, I know that you have probably some more capacity to generate even higher energies, but do you see there being any benefit to building even more powerful facility? Like once upon a time in the U.S., there was a super collider in Texas that would have been even more powerful.
Absolutely, yes.
Than the
Yes.
Large Hadron Collider.
Absolutely.
Do you see there being any benefit to that, or with where we are right now, is there any other fundamental particles out there that you think can be found?
Well, you are touching, of course, a point which is extremely important. Excuse me. At the moment, the community is discussing about the next step. Okay, now we have discovered the Higgs boson. Now, in a couple of years from now, DLHC will run at higher energy than today, so we may discover new particles. Okay, but of course, we are already brainstorming about what will be the next machine. Will it be a collider, a linear collider, a ring? What kind of beams, electrons or protons? There are many possibilities. My immediate answer is yes, of course. We have discovered a new particle now. We will have to move forward. So we will have a new machine at some point. For sure, we'll need a new one. What will be the feature of this machine in terms of energy, in terms of beams, in terms of location? Where will it be located? In the US, in Japan, in Europe? We don't know. But it's really one of the most important points that is being discussed right now by the community. I see a hand there.
Yes, the 125 gigaelectron volts, was that predicted, or is that just where you found it in the data?
So it was predicted and it was not predicted. So the theory, the standard model, predicts how the Higgs boson couples to the other particle, but the theory does not predict the mass. However, over the last 40 years, as I mentioned before, but in particular over the last 10 to 15 years, experiments at CERN, at the previous collider called the Lab Collider, and at the Tevatron here in the US, or at the Electron Collider at SLAC, and other experiments in other contexts, have made a huge number of measurements. And so this number of measurements together, interpreted in the standard model, in the theory, really had predicted that the Higgs boson would be quite light. And 125 GeV is in the range which was compatible with all the other measurements. So we were expecting it to be quite light. We would have been very surprised to find it much higher in mass, because this would have not been completely consistent with the other data within the standard model. So we are very happy that it's so light, because there is no contradiction in some sense. And it's also in the good range also for predicted by some theories beyond the standard model, like supersymmetry, which is a theory that tries to address some of the other questions I mentioned before. So far, so good. There was another answer. Yes?
You mentioned the Higgs boson, and you also mentioned the Higgs field, I think. Can you tell me the interaction between the two and the significance?
Yeah, well, it's a very good question, because so in quantum mechanics, field is associated to particles and vice versa. So the Higgs boson could be seen as a perturbation of the field. Imagine the field to be water, the ocean, and the ocean to be extremely flat. Then you have some waves. So the waves, this perturbation of the fields, are the manifestation of the field itself, the particle that you produce. So in some sense, by colliding the two protons, we excite the Higgs field and we produce the Higgs boson. We have not observed the field. We have observed the particle, which in some sense is a manifestation of the field. Yes, there is a field. There is a field here. So the Higgs boson, essentially, the discovery of the Higgs boson indicates that the vacuum is not empty. That there is a field which permeates. Okay. Yes. Oh, a young person. Very good. Not that because you are old. Okay. Sorry.
So, do you think that the discovery of the Higgs boson will help you search for other particles such as the gravitron?
It will, it will not help us directly in the sense, it gives us some indication that there must be some theory beyond the standard model, because the fact that the Higgs is so light in the standard model is not really so cannot be understood, because in the standard model, the mass should be, how to explain it to you in a simple way. Let's say, it's very difficult to have a particle with a feature of the Higgs boson in the standard model so light. So you need a little bit of acrobatics in order to be able to have it. So it will be much more natural to have a particle like that in physics beyond the standard model. So we think that the fact that it's so light is an indication that there should be new physics. So in that sense, the fact that we have discovered it and it's so light give us hope that give us another indication that points toward physics beyond the standard model. Does this answer your question? So I see 1, 2. So can I take first the young person here? Sorry again, but he's younger than you. So.
Yes, I was wondering what is currently known as the spin of the Higgs boson.
Oh, these people are really well prepared.
I've heard that it's rumored to have zero spin, which would imply that it's a scalar particle, and therefore the first elementary scalar particle.
Yes, very good. Exactly. So, excellent. So, elementary particles have some features called quantum numbers. Like can be like for a person could be the color of the eye, etc. And one of these of the features of the particle is called spin, is associated with a kind of intrinsic rotational motion. Now, the elementary particles that we knew until the 4th of July we knew 16 particles. So the Higgs boson is the 17th particle we discovered, okay? 16 particles fall into two classes. What we called matter particles, so-called because some of them contribute to ordinary matter. Electrons and quarks are matter particles because they are a constituent of matters. And their spin, so their rotation, the value of this rotational feature is 1/2. And then we knew another class of particles, so-called gauge boson. These are the particles like the photon or the W and the Z boson, which are responsible at the elementary level of transmitting the forces. And this particle has spin 1. The Higgs boson is predicted to have spin 0, so to be a scalar, as it's called in technical jargon, in technical language. Our measurement, I didn't show anything. I don't have, well, I have perhaps a slide or two, but anyway, our data clearly favor the spin 0 hypothesis. Okay, so now if we confirm that this is an elementary particle, which the data indicates is pretty much the case, if we confirm that it's a spin 0 particle, so a scalar, this will be the first elementary scalar ever, which is also very important because it has also some consequences on the evolution of the universe and the way the universe expanded after the Big Bang, where some scalar field, according to cosmology, have been involved, and so the fact that scalar field exists, I think, is a very good indication that this could be. Other difficult questions? There were two hands over there.
Does the discovery of the Higgs boson change at all string theory, or have any impact on string theory?
String theory is far, far away from us. So string theory sits at a very, very high energy scale and doesn't have a huge amount of predictivity at our energy scales. However, there may be some so the Higgs boson itself doesn't tell us much about string theory. However, string theories are some components that can be at least tested at the LHC. So string theory contains supersymmetry, which is this physics beyond the standard model. So if you discover supersymmetry, it's a kind of indication that we are more or less in, not that string theory is exact, but that that it is true or correct, but that at least some of the elements of string theory are true. Of course, if we don't discover supersymmetry at the LHC, doesn't mean that supersymmetry does not exist. It may well exist at a very high energy scale. Second, string theories have more than 3 space dimensions. So if we discover at the LHC that the world has more than 3 dimensions, perhaps 7, which is the number preferred by string theories, then will be another indication which points in that direction. But there is no direct implication, I think, of the Higgs boson with string theory, except that it doesn't exclude it. And then your neighbor, I think, had a... there, yes.
It took 20 years to discover the first Higgs boson, and now it seems that you're finding them on a fairly frequent basis. What changed between no Higgs bosons and plenty of Higgs bosons?
You mean the fact that we observe many Higgs bosons? We observe actually, well, we observe the same particle, but of course it's produced many times in the collision. So we are not observing different Higgs boson, but it's always the same, like observing many electrons or many photons, but it's always the same particle, okay? Did I catch your question?
No.
Yeah, so this is what I thought.
I think it's mainly more the advancement of technology has allowed us to detect the Higgs and produce the Higgs.
Yeah, okay. So, well, this is what I said at the end. We would not have been able to observe the Higgs boson if we had not developed an accelerator which can reach these energies. Okay, so if we had not developed superconducting magnets, which are now used, of course, in industrial application, if we have not developed detectors which have also some application elsewhere, I don't know if this is what you mean. Okay, so yeah, of course, in order to be able to discover the Higgs boson, we had to develop instruments that, of course, have now wide applications in other fields. And so, of course, it has changed our world also in another sense than just pure knowledge.
We have time for one more question.
And we have 2 ends, 3 ends, 4 ends, so how are you going to do? You choose now then. I want to take the responsibility.
All right, so with the discovery of the Higgs boson, do you think there are any other theories or models other than the standard model theory that can be further researched and supported?
Yeah, so also a very good question. There are some models that can be supported and some models which are disfavored. So, for instance, supersymmetry, this theory beyond the standard model, which many, including myself, like very much, but because it allows at the same time to address many questions, okay, so it will be very economical. A light Higgs like the one we have discovered is perfectly in agreement with the prediction of supersymmetry. So the only thing which is a bit annoying is that we didn't observe any supersymmetric particles so far, so it may be because it's a bit heavy. On the other hand, there have been until recently, other theories that have been more or less fashionable, called Technicolor, ComposeNet, etc., which actually predict a heavy Higgs boson. So a light Higgs boson is quite disturbing for them. So it's quite really, it's not, these theories are not really so fashionable any longer. So yeah, this discovery in some sense has already created some favoritism in the theory landscape.
Can we thank Dr. Gianotti again for her talk?
Thank you.